I want to present to you some of the work that I've been doing in collaboration with some people at my university, University of São Paulo, and also with Mauro Paternostro, which is essentially on this notion of irreversibility. So I'll spend quite some time talking about what irreversibility means, and then we'll move into quantum systems and see what kinds of new features appear when you talk about irreversibility in the quantum world. Okay, so we start with the second law of thermodynamics. And so for those of you who were in Santa Barbara in June, you may have seen these videos from Eric Lutz's talks. So the idea is that the basic laws of physics are all reversible. However, the phenomena that may emerge from them can be irreversible. So this is one example of a dynamics which is essentially reversible. And you can tell that it's reversible because you don't know if the video is playing forward or backwards. But now, if you look at this one, then this is clearly an irreversible dynamics because you can tell for sure that the video is playing in one direction of time instead of the other. So even though both of them are phenomena that are described by Newton's law of motion, you clearly see that one of them has an asymmetry in time and the other one doesn't. And that sort of motivates this idea of irreversibility. Oops, what did I do? I did something that I shouldn't, sorry. Let's try again. Yeah. Okay, so do I have the stick, the big stick? Yeah, here it is, okay. Okay, now it's better. Okay, so irreversibility, this notion of irreversibility is very important, both from a fundamental as well as from an applied point of view. So it really touches on some deep questions about physics, but it also is crucial if you want to describe several applications from electronic devices to heat engines and so on. So how do you quantify irreversibility? Well, in thermodynamics, the situation is usually quite clear. So you start with Clausius inequality, which essentially says that if you take any process, any physical process, and you monitor the entropy and the heat that's exchanged, then the change in entropy is always larger than the heat divided by temperature. That's like basic textbook thermodynamics, right? So based on that, we define entropy production as the difference between delta S and minus delta Q over T. And therefore, because of the Clausius inequality, that is always larger or equal to 0. And we learned in thermodynamics that this is 0 if and only if the process is reversible, right? So this is the sort of standard narrative in thermodynamics. For the purpose of this talk, I will mostly consider rates. So I'll use these three equations quite a lot, and I want to explain them in some detail. So essentially, instead of talking about a process and a delta of something, I'm going to talk about ddt of stuff. So I will define the rate of change of the entropy production as the entropy production rate. And I'll also call that guy, which is essentially the rate of change of the heat divided by temperature, that's usually called an entropy flux. So that's a name that people give because it's related to a heat flux, and so you call it entropy flux. So I think that this panel sort of illustrates that you have three quantities, and all three of them are different. Entropy production is not related to the change in entropy of the system. Because the change in entropy, the SDT, may have a term related to an entropy production, but a term related to an entropy flux. So you really have, when you want to consider irreversibility, you shouldn't look at the SDT, you should look at the entropy production, right? And here's an example, which I really like. It's perhaps the simplest example that you can imagine. You just take a RL circuit connected to a battery. And you assume that the resistance is dipped in a heat bath at some temperature T. And then if you study this model, what you'll find is that as soon as you turn on the circuit, things will start moving around. So for instance, the entropy will change, some entropy will be produced, and some entropy will flow to the environment. And so that's an illustration of how that happens. Now, if you wait long enough, you may even reach a situation where dsdt is 0. So the entropy is not changing anymore. The circuit just stabilized in a steady state. But this steady state is not an equilibrium steady state, because as long as there is juice in the battery, you will constantly be putting current in the circuit that will constantly be dissipating energy in the resistance. So this is an example of a non-equilibrium steady state where even though the entropy is not changing anymore, you're still producing entropy. The only thing is that this entropy that you produce flows all the way to the environment. So this is important to distinguish between entropy production, entropy flux, and entropy itself. Okay, now why is entropy production important? It is very important, for instance, because it determines the operations of a heat engine. So we're going to go here through a calculation that I think is very simple and very beautiful. So we're going to consider this engine where you have a hot bath, you have a cold bath, and you want to do something with them to extract some work, right? And now I kind of realize that that thing looks like a person that is very in distress or something, very worried about something, but okay. It was supposed to be an electric outlet. Okay, so here's how it works. So let's first look at this engine from a steady state perspective. So we write the first and second laws. The first law says that the rate of change of the energy is heat, heat, and work. And that's 0 because I'm assuming steady state. So the engine is operating in a steady state. The second law says that the ds dt is pi plus flux, and that is also 0 because I'm assuming a steady state. Right? So I only use these two facts, and now I compute the efficiency. So the efficiency, I define it as the work rate divided by the heat rate. Then I use the first law to eliminate W here. I get this guy. And then I use the second law to eliminate the cold QC, the heat to the cold bath, and I get this guy. And now this result, I know it's very simple, but it's extremely interesting. You see that the efficiency of an engine is essentially the Carnot efficiency minus something proportional to the entropy production. So this is why entropy production matters. Entropy production is the reason why your engine will not have the Carnot efficiency. It will have an efficiency that is lower than the Carnot efficiency. It's because of entropy production. So this is one example where entropy production directly enters in a very practical way. It really determines, quantifying entropy production tells you something about efficiency of a heat engine and how far away you are from Carnot's efficiency. Okay. However, entropy production is not a physical observable. You cannot associate a measurable quantity to entropy production. So what you need to do is you need a theoretical framework. You need some theory to try to associate entropy production, this sort of abstract concept, with some observable quantities. And there are many theoretical frameworks. For instance, Onsager has the Onsager theory of transport all the way back in the 30s, where that's where it all started. And so on, depends on the context. There are many theoretical frameworks. There is one which I really, really like, which is this approach by Schnackenberg, which considered classical master equations, so rate equations for some probability Pn. So you have a system with some discrete set of states, Pn, and you have just a Markovian equation with some transition probability W. This can describe anything from a physical process to something that is not physical at all, but for simplicity, here I'll consider the situation where these transition rates, W, they satisfy detailed balance. So they're essentially related. The transition rate from going from one state to the other and backwards are related to the equilibrium probabilities. This happens quite often in most physical systems, and I'll assume this just for the sake of the argument here. And also, I will define what I call entropy. So here I'm going to define entropy, or Schnackenberg defined entropy as just the Shannon entropy of the probability distribution, right? Okay, so now if you do that, and you just write down the SDT and substitute the master equation, you get this formula. You get that the SDT is a term that is clearly a entropy flux plus a pi guy, and this pi guy is given by this strange formula, which is always non-negative. So this function, even though it may not seem so, it's always non-negative, and it's 0 if and only if the system is in equilibrium. However, there's a much nicer way of writing this formula, which Schnackenberg didn't write, and to be honest, I've never seen anyone working in classical master equations to really write it this way. Although for a community in quantum information, it would be very natural. You can write the same formula like this, as the rate of change of the classical relative entropy, where S is just the Kullback-Leibler divergence of the probability distributions. And this formula gives a very, very nice physical interpretation of entropy production. So essentially, the idea is this. You have a master equation which describes the interaction of a system with some bath. And so eventually, the system will relax to equilibrium. It will start in some arbitrary state, and it will relax to equilibrium. Now, the way the system does that is by adjusting the populations. So we have these probabilities, these populations, and that will evolve in time until the system equilibrates. And so the entropy production rate here is seen to be nothing but the rate of change of how far the system is from equilibrium. So if you interpret the relative entropy as a kind of distance, essentially you're asking how is the system approaching equilibrium? How is it relaxing towards equilibrium? And so this gives a neat interpretation of entropy production. Okay, now what about quantum systems? Well, when you go to quantum systems, things become much more complicated. You have many classes of processes that you can consider, and there is no unifying theory that works for all of them. There's one class of processes for which the exact same spirit works, which is this idea of a Davies map. So some of you may have seen a Lindblad master equation. So this would be a Lindblad master equation for amplitude damping for a qubit. And this is an equation, I'm forgetting about Hamiltonians for now, but this is a class of equation called a Davies map. And a Davies map is very similar to Schnackenberg's approach. And in fact, it has been shown by Spoon in '78 and then again and again by several authors that the entropy production rate is exactly the same formula we had before. But now, instead of having the classical relative entropy, you substitute it by the quantum relative entropy between the current state of the system and the equilibrium state. What is interesting also about these Davies maps is that they have this notion of Ein selection. So in the Davies maps, the environment selects a preferred basis, which is essentially the energy basis. And this means that the populations of the model in the energy basis, they evolve independently of coherences. So before we just had populations. Now we have a density matrix that has populations and coherences. But for Davies map, these two evolve independently. And in fact, the populations evolve exactly according to a classical master equation. So one thing we can do, for instance, is very simple. We can just split up the quantum relative entropy into the classical relative entropy plus the relative entropy of coherence, which has become quite popular more recently due to resource theories in quantum information. And then if we do that, then the entropy production is split into two terms. And again, this is a very simple result, but the physics is very beautiful. Essentially, you're saying that you're producing entropy. You have an irreversible process because you're adjusting populations, because the system is thermalizing, but also because you're losing coherence. The bath destroys the coherence in the system, and that is an irreversible process that produces some entropy. It's interesting to note that for this particular class of maps, the coherence does not affect the entropy flux. So if you start a system with coherence or not, the amount of heat that will flow to the bath will not matter for this particular map. However, the loss of coherence still contributes to the entropy production. So that's, again, an interesting way of distinguishing between entropy flux and entropy production. OK, so now we get to the main part of my talk, which is a formulation of entropy production in terms of quantum phase space. So to start, let's consider a kind of Lindblad master equation that is very, very popular experimentally, which is this leaky cavity Lindblad master equation. So if you have an optical cavity and one of the mirrors is semi-transparent so that photons can leak out of it, you can describe that very well by this kind of Lindblad dissipator, which is A here is a bosonic operator, an annihilation operator, and you're essentially describing the rate at which photons leak out of the cavity, and gamma is essentially that rate. Now, this kind of Lindblad dissipator can be thought of as a particular case of this guy, which is a finite temperature dissipator. So this would be the Lindblad master equation that you would use to describe the thermal processes of a harmonic oscillator or a bosonic mode in general. And that one can be viewed as a particular case of this one at 0 temperature. So this n, I apologize, I forgot to write it down. Maybe I should. This n is just the Bose-Einstein distribution. So it's 1 over e to the beta omega minus 1. And so 0 temperature means essentially n equals 0, 0 excitations, and then you recover that case, right? Now, this is a very common Lindblad dissipator. It's used to describe many experiments in many areas of quantum physics. However, if you just try to apply everything I just told you before, you'll find that both the entropy production and the entropy flux are infinite. And that is very frustrating because they're infinite in a very silly way. The entropy flux is just infinite because it's 1 over t here and t is 0. And the entropy production is infinite because the relative entropy with respect to a pure state can be infinite if the guy on the right is a pure state and the ground state is a pure state. So it's very frustrating that they're just infinite. And they're not infinite in a fancy way. They're infinite in a very silly way. And what is worse, both of them are infinite, but the SDT is not infinite. The entropy never diverges. If you just consider the dynamics of this, you'll never find an infinite entropy. So it's very strange and a little bit annoying that you have this kind of result. In fact, there's even a better argument. So suppose you just consider these dynamics and you start in a coherent state. So you have a harmonic oscillator, you start in a coherent state. And then you let it go, you let it evolve. What will happen is that it will remain in a coherent state throughout. So this is a very special example, right? I mean, usually this is not true, but this is a very special case. So if you think in terms of phase space, you have a Gaussian that's like all the way out here, and then you let it go, and it just spirals out with some frequency omega of the oscillator and some damping rate gamma. So you see, this is an example where you start in a pure state and you continue in a pure state throughout. So the entropy is 0 at all times. Entropy is 0, 0, 0, 0. But at each instant of time, the entropy production would be infinite and the entropy flux would be infinite. And that is very frustrating. And then you can say, well, maybe it's not really 0 temperature. Maybe the temperature is very small. But still, you would get a situation where the entropy is 0 and the entropy production is very large and the entropy flux is very large, just so that they cancel that you get something that is 0. So that's, again, certainly points to the fact that there's something missing here. Yeah, oh, there it is. So what is the explanation? Well, the explanation is that we're trying to use thermodynamics to something that is not thermodynamical in the end. That's the point. I mean, we're trying to force a thermodynamical result. We started all the way with Clausius inequality, and we're trying to push it into something that has nothing to do with thermodynamics. That's the mistake in the reasoning here. And the point is that, yes, photons leaking out of a cavity, that's a bath. It's a bath in the sense of an open quantum system. But that's not a thermal bath. It is not a bath like a bucket of water. It's different. So we can call it a non-equilibrium bath or an engineered bath, sure. It's a bath in the sense of openness, but it's not a thermal bath in the sense that we're used to in classical thermodynamics. And in fact, in the quantum realm, we can actually engineer many interesting baths. So not only leaky cavities, we can talk about squeezed baths, where the bath has some squeezing. We can talk about the phasing. And we can even talk about spontaneous emission, which is a kind of bath at 0 temperature, and for which the same argument that I just gave would also break down. If you just consider spontaneous emission in vacuum, you cannot apply entropy production and entropy flux to that argument. It will not work. So that's part of the motivation for introducing these phase-space quantities, which is to be able to formulate the problem of entropy production in a way that is beyond thermodynamics. We're borrowing the ideas from thermodynamics, this notion of quantifying irreversibility, which I think is very valid and is very interesting. But they're trying to apply it to situations that are not really thermodynamical situations. So in our approach, what we do is essentially we work in phase space. So we introduce the Wigner function. And for simplicity, I'm going to talk here mostly about just one bosonic mode, but the extension to multiple modes is quite straightforward. So we define the Wigner function as a function of these coherent state variables, alpha and alpha star. In this way, and just to give you some examples, I guess I'm not sure if this is really necessary, but here are some examples of Gaussian states for a single mode. So you have the vacuum, you have thermal states, squeeze states, coherent states, and so on. And the interesting thing about moving to phase space is that you turn a Lindblad master equation into a Fokker-Planck equation. So now, instead of working with density matrices, you work with the quasi-probability. The Wigner function is a quasi-probability. And instead of having operators, you have now differential operators. So you have a Fokker-Planck equation. I just want to point out that the Fokker-Planck equation, even though it's written here in a sort of funny way because I use these complex variables, alpha and alpha star, it's essentially the same as a diffusion equation. So you see clearly that there is a term which is a first-order derivative, which is the drift term in a diffusion equation, and there is a term that is a second-order derivative, which is a diffusion term, right? And so here you see that the diffusion matrix is essentially, the diffusion matrix is essentially related to this n+1/2 here, which is the thermal population. Okay, another very interesting thing that one can do with Fokker-Planck equations is to write them as a continuity equation. So the same equation I wrote before can be split into this form, where I know it doesn't look like it, but this is kind of a divergence in the complex plane. I mean, if you write it down in terms of real and imaginary parts of alpha, this is nothing but a divergence. So this is essentially, I'm failing. Okay, I got it. Yeah, so this is essentially a continuity equation. It says that the DDT of a quasi-probability is related to the divergence of some current. So these J's, they can be interpreted as quasi-probability currents. They tell you that, W is changing in a certain point because you have currents that are entering and leaving that point at any time. So you have this nice current interpretation. And this is even more meaningful because you can also look at the steady state of this differential equation. Or the state where ddt of where the right-hand side is essentially 0. And what you find is that not only is the right-hand side 0, but in fact, the currents themselves are 0. So it's a stronger result. You could have a steady state where d alpha of this plus d alpha of this is 0. That would be a steady state. But here is stronger. You're saying that the currents individually are 0 in equilibrium. So we can actually define thermal equilibrium, so to speak, as the state that has 0 current. Is that state where if you put the system, no currents flow in phase space. And I think that has a very neat physical interpretation. And it's essentially this notion of detailed balance in terms of Fokker-Planck equations. Okay, and now for the final ingredient is that we cannot use the von Neumann entropy, so we introduce this idea of a Wigner entropy, which is essentially the Shannon entropy of the Wigner function. And the motivation for this is twofold. So first of all, before I say anything else, the Wigner function can be negative. So this only makes sense for Gaussian states. For Gaussian states, the Wigner function is always positive, and so this S will always be a well-behaved quantity. The biggest motivation for using the Wigner function is that actually for Gaussian states, this is related to the Renyi-Chu entropy. So this paper by Gerardo Adesso in 2012, they showed that for the set of Gaussian bosonic states, the Renyi-Chu entropy and the Wigner entropy are essentially the same. And so this gives, again, a very nice interpretation because the Renyi-Chu is, well, it's the purity essentially of the state. So it has an operational interpretation. Whereas the Wigner entropy also has a neat interpretation. If you think of W as a quasi-probability, you're essentially evaluating the essentially the entropy of that quasi-probability. So it's very natural to talk about it. Another motivation is that if you want to change this and not use the Wigner function, but use the Houssimi function, which is defined over there, you get something that's called whirl entropy. I don't know if I'm pronouncing that right, but maybe. And this whirl entropy has been studied for quite some time. In particular, it has also a nice interpretation in terms of sampling. So it's related to when you do measurements in phase space, you get this emerging notion of sampling entropy. And so there's a lot of work on this entropy being related to the amount of information that you can extract from your system and so on. Another nice thing, and this is just a side comment, about Houssimi functions is that you can extend it to spins. So you can define spin-coherent states, and then you can do everything that I'm doing here for spins as well. And this is discussed in this paper over here. It's not as elegant as for bosons, but you can also talk about spin systems. Okay, so now we have all the ingredients we need. We have a Fokker-Planck equation, and we have one definition of entropy that we are willing to explore. And what's nice about this is that now we can use several results that exist in the literature for classical Fokker-Planck equations. So the literature from the stochastic thermodynamics community is very large, and we can exploit some of those results. And essentially doing a calculation, which is just a few lines long, we find that ds dt is given by this guy over here, and plus the pi, where pi is given by this. And I personally think that these results have quite a pretty physical interpretation. So first of all, you see that this is quite close to what we're used to that I was showing before, where you had heat divided by temperature. And I'll explain a little bit about this more in a second. Also, the entropy production here is directly related to the currents. It's essentially a kind of average of the currents. And so it will be 0 only if the system is in equilibrium, only if there is no current. So you directly associate these J's, these currents, as being the microscopic quantities that generate irreversibility. Microscopic in the sense of phase space. So you have, like, in each point in phase space, you have a current, and you're essentially doing a sort of average of these currents, integrating them, and that gives you an entropy production. And also, this is also clearly positive as long as the Vignette function is positive. So another very nice thing is that you can write the same result here, this guy. You can also write it as a relative entropy between Vignette functions, which is sort of intuitive and expected. And also, the entropy flux, as I was saying, so it's defined like this. If you expand out the heat rate, you can write it like this. And what is nice about it is that for high temperatures, this omega n plus 1/2 is approximately T. So you recover the von Neumann results. So if you're working at high temperatures, it doesn't matter if you use the Vignette entropy or the von Neumann entropy. They both give the same results. However, if you now move to the opposite limit and go to 0 temperature, then they both remain finite. And then you have an operational quantity that you can use to estimate irreversibility even at 0 temperature. Okay. Yeah, and I focus here on thermal reservoirs, especially because of the applications I'm going to show next. But I mean, the extension to other kinds of engineered baths is extremely straightforward. Essentially, I mean, this expression is almost unaltered. You just need to change what is J, what is the current. So if you want to have a squeezed bath or a dephasing bath and so on, you can have the same formulation for different kinds of environments. Okay, so now as a first extension of this, we're going to move to this idea of non-equilibrium steady states. So now, up until now, we had one system and one bath. So now we want to have a system that has multiple parts which are connected to multiple baths. And in this case, what is interesting is that the system will never reach equilibrium. Because as long as these baths have different temperatures, there will always be currents from one bath to the other. So the system will never equilibrate. In particular, we're going to consider local master equations for definiteness, or what some people call boundary-driven systems. We'll essentially assume that we have a chain of harmonic oscillators, for instance, which are coupled to two baths, one at site 1 and one at site L. So you have some chain, and you have two baths at either side. And then, of course, you can go to a Fokker-Planck equation. It's very, very similar. But the important part is that now you're going to have some unitary contribution. I didn't write down this guy explicitly, but it's essentially whatever comes from here, right? When you move from this to this, whatever things you get here, I put them there. And now the entropy balance equations will be that, the rate of change of the total entropy will be given by a sum over all channels, over all damping channels of the entropy production and the entropy flux of each channel. So that is interesting that you can address how much entropy is produced by each channel and how much entropy flows to each channel. And I think that's valuable. The results seem very similar to what I've shown before. The entropy flux and the entropy production, the formula seems almost identical. However, there is one subtle difference. So if I take now these formulas for the entropy production, I mean, it's the same one I had before. I just put I here, like everywhere. If you take this result and you compute the total entropy production as just the sum of these guys, you find that it's not the relative entropy. And it cannot be the relative entropy because this guy is a DDT of something. And if you're in the steady state, then DDT of whatever must be 0. So it must have a new contribution. So this guy will have a transient term. This guy will dominate transience evolution. But when you reach a steady state, this guy will be 0. And then you're left with this guy. And this guy depends on the unitary. So this is actually, I mean, in a sense, it's a bit surprising that usually we associate unitaries with reversible dynamics. And so it's a little bit weird that we have here a unitary term appearing in the entropy production. However, the point is that the entropy production only exists because there are currents from one BEF to the other. And these currents exist because of the unitary connections. If you didn't have these unitary connections, these guys, for instance, then you wouldn't have a current. You would just have independent systems. So it's really, in the end, the unitary terms which are responsible for maintaining this non-equilibrium steady state. Sorry, you want to think? So it's essentially these unitary terms which are responsible for maintaining a entropy production in the ness, in the steady state. Okay, and now finally, I want to get into this result. Oh, this is supposed to be 2019. Sorry, this paper came out in the beginning of the year. So what is done in this paper is we found two systems which were controlled quantum systems that we could actually assess and determine the entropy production in a non-equilibrium steady state. And systems where you can actually see a quantum contribution to entropy production, which I think is an interesting goal to understand what is classical and what is the genuinely quantum mechanical contribution to irreversibility. So one of the systems was an optomechanical system. The experiments were done in the group of Aspelmeyer in Vienna. And so essentially, the Hamiltonian is a cavity, so an optical cavity interacting with a mechanical oscillator. And you also have, so this is the optomechanical coupling, and a pump term. So this is how you pump photons into the cavity. And the master equation will have two dissipators. So this falls really into that category of non-equilibrium steady state with two BEFs. But one BEF is the leaky cavity. So one BEF is essentially determined by the fact that, this mirror is semi-transparent, so photons leak out of it. And the other BEF is a mechanical BEF. It's essentially related to the fact that this mirror can vibrate here. And so there is some damping. It's just damping of the mechanical mode. The other system is in the group of Timo Eslinger in ETH. It's essentially a BEC, which is trapped in an optical lattice and also inside an optical cavity. So in this case, you again have a mode for the optical cavity. And the other part of the Hamiltonian will be a Bose-Einstein condensate that you approximate as being essentially a two bosonic mode. So you have a ground state and a first excited state of the BEC. And you work in this low energy subspace where you can approximate it to be something like this. And now again, you have master equation with two BEFs. One BEF is again the leaky cavity, and the other BEF is a collective dissipation of the Bose-Einstein condensates. So you have these thermal losses that appear in the BEC, and they contribute to an effective thermal dissipator. So in both cases, you have one guy which is essentially a thermal dissipator, and one guy which is essentially a zero temperature dissipator. Now, what you do is, first of all, you Gaussianize. What's interesting about these systems is that they can be Gaussianized. So you can operate in a regime where they behave, even though neither of these Hamiltonians, neither this nor this, are Gaussian Hamiltonians. They are cubic, so they would not fall into this Gaussian framework that I showed you. You can find operating regimes where they do, and then you Gaussianize them. And so essentially everything becomes related to some two frequencies of the two bosonic modes, and some coupling constant G, which is the interaction between the two modes A and B. So now you're really falling into precisely this scenario over here. For the case of the mechanical oscillator, the mode B is a bit more intuitive. It's just the fluctuations of the mechanical vibration. For the BEC, the mode B is a bit more intricate. It's related to collective excitations of the BEC. So I mean, the meaning of B here is not so straightforward. And also another comment that I think is worth mentioning is that since both of these experiments use these leaky cavities, you cannot use the von Neumann approach. So these are situations where really this Wigner entropy approach is the only approach we have today for estimating entropy production. You could not apply the standard thermodynamic results. And this is part of the motivation why we developed this approach in the first place, was looking for some way to estimate entropy production in these processes. Okay, and now here are the results. So this is for the optomechanical system. So this is the entropy production as a function of the coupling strength. So this is a normalized coupling between the optical and the mechanical modes. And what you find is that essentially the entropy production increases with top-to-mechanical coupling. It does so because the current increases. The more strongly coupled they are, the more heat flows from one to the other. And so the entropy production also increases. This curve over here is one of the contributions to the entropy flux. And we're quite happy that we could extract that, because if you look at the scales here, this is entropy production is in gigahertz, and this is in hertz. So you really have one bath, which is the leaky cavity, that is producing most of the entropy and dissipating most of the entropy. But we can also assess experimentally the entropy that is flowing to the mechanical environment. And that's quite interesting.
So, what are the error bars?
What are the error bars? Well, I don't have a perfect answer because I didn't do an experiment, but I know that they're related to, first of all, really the fluctuations, but also the fluctuations in the parameters, because to estimate this guy, you need to assume a bunch of parameters, and the values of those parameters are also not perfectly known. But that's sort of the best answer I can give, yeah. And these are the results for the BC. So the BC, it has a quantum phase transition. It's the critical phase transition of the Leaky model. And the entropy production diverges at the critical point. And again, here we can also estimate the entropy flux to the incoherent BC bath. So we have these two contributions. Again, you have a huge, in this case, not so much, but you again have a kind of separation of scales, where here's like 300 kilohertz and here's hundreds of hertz. But now you have you still can estimate both of them. And also, I wanted to make a comment about this, which is that it's quite interesting that the entropy production diverges. So I'm formerly from, statistical mechanics community in critical phenomena, and it turns out that the entropy production in classical systems never diverges, but in quantum systems apparently it does. So this is something that one of my master students is working on right now to try to understand when will a quantum contribution to the entropy production give diverging results, and when it will not. Okay, so essentially that's pretty much what I wanted to say. I think that this notion of irreversibility, I think it's a very valid question to understand when is a process irreversible or not, and what kinds of features give rise to irreversibility in quantum processes. I think it's a nice way of bridging between quantum information and non-equilibrium physics, which is something I'm particularly interested in. And I think that this idea of understand and quantify is a good approach to it. So I'm really interested in really understanding where irreversibility comes from, but I also want to be able to quantify it in an operational way. This phase-space formalism that I showed, gives interesting insight in terms of these currents and how everything that is usually treated in the level of density matrix can be viewed from the perspective of phase space. But it is also something that is useful to quantify entropy production, because there are some scenarios like the leaky cavities and the experiments that I showed for which this phase space formalism is the only formalism available out there. So I guess that's it. Thank you.